Next, we have David Burton, soil scientist and professor at Dalhousie University, and he's actually very distinguished, a distinguished research professor. He's also Dalhousie's director of the Center for Sustainable Soil Management, and he's also fellow of the Canadian Soil Science Society. And I also see he's put on a jacket for this presentation. Awesome, Dave. So Dave is going to share with us his thoughts on the role of soil management in the path to net zero. It's all yours, David.
Okay, thank you very much, Mariel. It's a pleasure to be here. I'm just getting my screen up. I'm assuming you can see that appropriately.
Yes, Dave, we can.
It's an honor to be here, and it's an honor also to follow up from Dr. Henry Jansen's talk, and much of what I'm going to say is going to echo some of the points that he's made in his talk. I'm going to talk about the role of soil management in the path to net zero, focusing a little bit more on nitrogen, but also talking a little bit about carbon. But I want to start with a little bit of context. Again, some of this is some of the material that Henry went over. Are we currently on the path to net zero? It looked promising up to about 2011, but we've started to go in a different direction. And again, Henry presented some more current data that says that we're continuing in that other direction to some extent. Why is that? Well, if we break down our emissions, we can see that nitrous oxide and methane are our major contributors in terms of emissions. We do have this soil carbon sink that at one time was increasing, but now seems to be decreasing a little bit. So the balance is still a positive emission. I want to talk a little bit more about this nitrous oxide curve, but I also want to reflect on the fact that much of this carbon storage was in Western Canada, in Prairie Canada. And I think there still are opportunities in Eastern Canada to figure out how we can put more carbon in our soils. And I'll come back to that point later. But let's look at nitrogen for a little bit. Nitrous oxide emissions are increasing, and that's very much paralleled by nitrogen fertilizer use, not surprisingly. It's primarily from nitrogen fertilizer use, not exclusively, but primarily. Well, where are we using that nitrogen? Primarily in Prairie Canada, in Western Canada, and the amounts of nitrogen have been increasing much more dramatically than they have been in Eastern Canada. Why is that? It's largely related to canola production. And I think there's a couple of really important things to note in terms of that. Partly that's the increase in acreage of canola produced, but also we're increasing the amounts of nitrogen applied to that canola. But if you notice here, I have the canola production in gray and the fertilizer use in orange. That slope of that canola production is much greater than that of nitrogen use. So we're actually getting more efficient at producing that nitrogen. And Tim talked a little bit about emissions intensity, and that's probably an important thing to reflect upon. The other really important thing to reflect upon is, why are we producing so much canola? Is it because all of a sudden we like canola oil? Well, part of it is for the food market, but another important part of it is also to support the bioeconomy and biofuels to replace fossil fuels. Okay, so that's another part of this consideration when we talk about the path to net zero and boundaries. Where do we set the boundaries and increase the production of N2O from agriculture if that's producing a crop that offsets fossil fuel use? Needs to be part of that calculation. So one of the important points that I want to build on in terms of some of Henry's points is, I think we have to rethink what are the products of agriculture. I think for too long, we've traditionally thought of plant yield and animal production as our sole products. And that's no longer, and oftentimes we only measure them in terms of total mass, not the quality or the nature of that product. But I think we have to move to a much broader concept of what is produced on the farm to include environmental goods and services. An important part of that recognition of that being a product of the farm, it needs to be also that something that farmers are compensated for. It must make economic sense for the producer to adopt these practices to produce a value product and be compensated for that product. Some of the environmental goods and services that we can think about include storing carbon, building soil organic matter. I'm going to make the point that I think the capture of CO2 into soil organic matter is a very beneficial thing, but it's not nearly as important as the actual value of that soil organic matter once in the soil in terms of increasing the resiliency of our systems, resiliency in particularly in the face of climate change. Reducing nitrous oxide emissions, that's another important environmental good and services. But that is also reflected by more efficient nitrogen fertilizer use, and I would say improved profitability. I've already mentioned biofuel production in canola. Well, the offsetting of fossil fuel use by the production of biofuels, that's another important environmental good and services that is often associated with either corn or canola production. And we haven't talked very much about biodiversity, but we will later in this session. Habitat protection is another really important environmental good and service that we don't often reward the producer for. And if we want these kinds of environmental goods and services to be implemented on the farm, they have to be part of the production system. Let me give you a quick example. Here's a typical nitrogen response curve that we might see for any one of a number of crops. This happens to be an example of corn grain production from the Elora Research Station over a number of years. And we see a very classic curvilinear response. Adding a small amount of nitrogen results in a fairly large increase in nitrogen yield. Note also that adding zero nitrogen still also produces rather significant nitrogen or corn yield. We sometimes forget that we can produce crops even if we don't add nitrogen fertilizer, but adding a small amount resulted in a big benefit. But at some point, that benefit tapers off and this curve becomes curvilinear. That input curve is not curvilinear, it's linear. So each increment is simply a linear increment of the previous one. And it's also important to note that the environmental impact of that nitrogen use is also curvilinear, but in the opposite direction. And it's really important to realize that as we move up to larger amounts of nitrogen, there's a disproportionate influence of that additional nitrogen on nitrogen losses. And that's important to realize. At one time, we used to farm down here. Before the advent of nitrogen fertilizers, we had very modest inputs, very modest yields. As a result of the Green Revolution, we dramatically increased that situation. Now we're farming up here. We're really pushing our systems to the max, going for maximum yield, maximum inputs to achieve that maximum yield, pushing the system. And in some cases, that's causing soil degradation and compromising the sustainability of our systems. It's my argument that we actually need to be farming down here, somewhere in the middle, in a more moderate place where we're not only recognizing the value of the yield produced and pursuing maximum yield, but we're also recognizing maximum profitability, which often occurs at a fertilizer application rate less than that achieves maximum yield. And we're also recognizing the value of some of the environmental goods and services and the inherent climate resiliency that we can build into our system as a result of enhancing soil health. So I guess I'm trying to emphasize the same point that Henry made earlier on, is that we need to rethink our agricultural systems and stop thinking about yield as the only product we produce. There's a vast array of products that we produce and all have important value. So let me talk a little bit about soil carbon. So what are some of the values of, or how are some of the ways in which we can enhance soil carbon while increasing the diversity of our cropping systems? Henry talked about perennial crops and how we can achieve some modest amount of perennial-like behavior by using things like cover crops or intercrops. Having plants on the landscape for a longer period of time. Very important opportunity. Diversifying our crop rotation so we have more diverse root systems, greater use of legumes that allow us to use less nitrogen fertilizer by taking advantage of biological nitrogen fixation. But most important, or perhaps maybe not most importantly, but importantly also recognizing the value of those crops to subsequent crops in terms of legume credits, including periods of perennial crop cover. Again, perennial crops are a way in which we can stabilize soil, build soil organic matter for more root growth. We've had some success in some potato production systems in Prince Edward Island where adding an extended period of perennial crop followed by more intensive production and returning to an extended period of perennial crop can build soil organic matter. So perennial crops don't have to be for decades. Sometimes they can be for several years, such that we're leaving that soil undisturbed and allowing that perennial crop to build that soil organic matter. Reducing soil disturbance. I think we have to find ways in which we can establish our crops and maintain our crops by whilst at the same time disturbing the soil. The excellent example of that was no-till in Prairie Canada. It resulted in a large amount of increased soil carbon sequestration because we were allowing the roots to decompose in place. We were not disturbing that soil. We have to remember that most of the organic matter that's formed in soil comes from roots, not shoots. And if we can leave those roots undisturbed in place, they're more likely to make organic matter. Rotational grazing. Others, I think, are going to be talking about this as well. Another opportunity to use the way we manage the land to manage the roots and manage their opportunity to make organic matter. A really important opportunity. And again, one of the really important aspects of building that soil organic matter is not the carbon storage. I think that's a yearly useful benefit, but more importantly, more value to our system is the resiliency that builds in our system. The soil and increase in soil health, the increased resistance to soil erosion, more water holding capacity. And as we're experiencing more extreme climates, we're going to need that climate resiliency. One caveat though is, and I'm going to keep coming back to this, is we need to make sure that we can capture these practices in our national inventory report. So our national inventory report reflects what we're doing to try to reduce our emissions and increase our climate resiliency. I'm going to turn to nitrogen. We've done centuries, but most importantly, decades of research on nitrogen. But one of the biggest problems we have in nitrogen right now is we're not measuring the state of nitrogen on our soils very much. We are really fortunate in that there's a number of new tools that have been introduced and concepts in terms of the 4 R's of nitrogen management that the fertilizer industry has introduced, focusing on the right rate, the right time, the right product, and the right placement of nitrogen. I would add a 5th R, the right rotation, because that fertilizer use occurs within a crop rotation. But one of the biggest challenges we have in implementing these kinds of practices effectively is we're not currently measuring the state of nitrogen in our soils. And I'll show you an example of that in a moment, some of the work we've been doing in Atlantic Canada. So in terms of some of the 4 R's that I think are going to be key in understanding or I shouldn't say understanding, in reducing our nitrous oxide emissions include sources. Enhanced efficiency fertilizers have gotten the spotlight. I think they're an important part of the solution, but only part. Placement, variable rate nitrogen use, I think has tremendous opportunity to fine tune the need for nitrogen within the landscape with its supply. Not all parts of the landscape are equally yielding. Therefore, we shouldn't be supplying nutrients in the same amounts within that landscape. Timing, split application, delaying nitrogen supply until the point where the plant needs it has a tremendous opportunity to reduce N2O emissions. And perhaps most importantly, rate. Too often we are under the concept that some's good, more's better. We need to add that insurance nitrogen. Next year is going to be that good year. Often it isn't. Our historic yields the yields over the last 3, 4, 5 years are probably a good indicator of the kinds of yields we're going to be changing and receiving in future. And therefore we should be fertilizing for those yields. So in some cases, less can be more. And particularly because the profit curve, the difference between the cost of nitrogen and the value of the yield is a relatively flat response curve. So there's some opportunity to change nitrogen rates to reflect the environmental conditions and optimize profitability. But other really important considerations in rate is the consideration of soil nitrogen mineralization. And again, I'm going to come to that in a moment. Fertilizing based on realistic yields, and reducing our N rate to reflect the efficiencies achieved through the other 3 or 4 R's. Too often, if we're able to deliver nitrogen more efficiently, we should not need as much of it. So there is an opportunity for a modest decrease in nitrogen rate to reflect that more efficient delivery system. Again, another important point, we have to make sure that there are ways in which we can capture these activities in our national inventory report so that it's reflected in terms of our Paris commitments. I'm going to turn to an example of a project we've been doing in Atlantic Canada, where we've been trying to actually develop a test to measure nitrogen mineralization potential and use an understanding of the climatic conditions of, in this case, Prince Edward Island, to determine to what degree that potential is realized in terms of nitrogen mineralization during the growing season. So we happen to use what we call the biological nitrogen availability, or BNA test. It's just simply a 2-week aerobic incubation. This is a tool that the PEI Analytical Lab has implemented as part of their soil health testing package. And that measures the nitrogen mineralization potential. And again, we put that in the context of PEI's climate to estimate growing season nitrogen mineralization. And here are some of the results of some of those initial analyses. Over the last 2 years, the PEI Analytical Labs analyzed about 3,000 producer fields, soil samples collected from producer fields to produce this estimate of the rate of nitrogen mineralization occurring over the growing season. And I want to draw your attention to a couple of points. First of all, look at the incredible variability that we see over those fields. We have some fields that are 40 or 50 kilograms of nitrogen per hectare. We have some fields that are 300 or 400 kilograms of nitrogen per hectare. This is a variability in nitrogen supplying capacity that we're not currently capturing and not currently considering in our nitrogen management strategies. A lost opportunity. The other important thing I want you to note is that root crops here are primarily potatoes, and we have other grain crops. You'll notice some of them, their mean values are around 90 to 100. But when we have forage hay pasture systems with legumes in them, those mean values increase by about 30 or 40 kilograms of nitrogen per hectare. So we're seeing actually typical nitrogen mineralization rates characteristics of cropping systems, and in particular cropping systems that include legumes. It's important to reflect that information in terms of our nitrogen management. So my major message is we need to measure nitrogen mineralization, include it in part of our nitrogen management strategies. The other part of this system we've been using in Atlantic Canada is trying to measure the potential for nitrogen loss. We measure a in-season nitrate accumulation as nitrate exposure. We find that very much predicts nitrous oxide emissions. It's still a bit of a research tool, but we can also use measurements of crop yield and the nitrogen that is being removed, or the amount of nitrogen that remains in the soil after harvest as ways of saying how well do we do, and informing things like post-harvest soil nitrogen management strategies. Do we need to get a cover crop out there to absorb some of the nitrogen that's being lost? Tim showed one of the agri-environmental indicators relating to carbon accumulation. Well, here's another one, residual soil nitrogen. And again, we're seeing lots of red in Eastern Canada. We're putting more nitrogen on than we're taking off. So there's an opportunity to improve that system, to increase that nitrogen use efficiency and benefit from that. So the 4R strategy, the 4R system framework is a really excellent way in which we can bring more science. And one of the reasons why I like the 4R approach is it is based on sound science. I think our science is well developed in this area, but it puts that science into practice. But one of the things I really want to emphasize about this 4R framework is it has to be done, all 4 Rs have to be, or 5 Rs have to be considered simultaneously as part of an integrated solution. We can't cherry pick 1 or 2 of these practices and say, oh, I'm going to do that and that's all I'm going to do. We have to do an integrated consideration of the 4R. And I'm going to use an example again from Eastern Canada. This is potato production in Prince Edward Island. We did an on-farm experiment looking at 6 different farms across Prince Edward Island in 3 different years, where we considered three nitrogen management strategies: the grower's standard practice, or GSP, a practice where the grower replaced a part of their nitrogen program with an enhanced efficiency fertilizer, or finally 4R, what we call 4R plus, where they not only replaced a portion of their nitrogen fertilizer with an enhanced efficiency product, but they also reduced the rate to reflect the increased efficiency of that product and also the increased cost of that product. So we designed it so it was cost neutral in terms of their normal nitrogen program. And here we see that it had no effect on market yield. There was no significant decrease or increase in market yield as a result of the implementation of this 4R practice. In terms of their gross returns, again, no significant effect. In terms of nitrous oxide, there was a dramatic reduction. 4R, just simply using enhanced efficiency fertilizer resulted in about a 33% reduction in N2O emissions. But using that enhanced product in addition to a reduced nitrogen rate resulted in a much more significant N2O reduction, about 60%. So we have tremendous opportunity to reduce N2O emissions in these systems without affecting profitability. And that's one of the things that gives me optimism. And Henry reflected upon his value for optimism. I think mine's a little bit lower than his, but not too much. But the need for hope, and I think that's one of the messages I want to read. We also measured residual soil nitrogen, more variable, but again we saw less nitrogen remaining in the field in the fall as a result of the implementation of these 4R practices. So in summary, can soil management contribute to net zero? Yes, but only if we value the environmental goods and services, whether they be carbon storage, reduce N2O emissions, production of biofuels, or increase biodiversity, and return that value back to the producer so they can see the economic benefit of implementing these practices. And also all these practices, these actions must be captured in our national inventory report for them to have meaning to Canada as a country in terms of meeting our Paris Accords. And with that, I'll just put up a screen acknowledging some of the people that have supported this work, and I'll turn it back to Mario.
Great.
Thank you.
Thank you, David. Excellent and nice deep dive into 4Rs and other 4R plus and 5s.